Okay, so I'm going to present the second part of ships hydrostatics. So I'm going to talk about the metacenter, the metacentric heights that are pretty important for ships. So the easiest way to explain this is if I make drawings. So I don't draw very well, so sorry in advance. So as you can see, basically the ship is in equilibrium the moment that the center of gravity is opposed to the buoyancy center. So in a stable position, the center of gravity and the buoyancy center are on the same line, called the center line. And so in this position, the forces cancel each other out, which means the ship remains stable. The problem is when a disturbance occurs, because when a disturbance occurs, the ship rotates, of course. Maybe not that extreme. And because there's not the same weight, because here the buoyancy depends on the weight of the ship that's submerged, right? So when the ship is rotated, the same weight is different. So the buoyancy center shifts automatically, like around here. It's not a very good drawing, but so this is the new buoyancy center, but the gravity, the center of gravity is not going to change because the weight of the ship hasn't changed. So it's still going to be around here, right? So sorry. Okay. So that means there's not going to be the same. Yeah. So we still have the same center line here, but since the center of buoyancy has changed, you get a new line that starts from here and that goes in the same parallel direction. And so where these two lines intersect is called the metacentric center. And so that's pretty important for ships to determine because it allows them to know how much the ship is going to rotate, because since there's a new buoyancy center and these two forces don't cancel each other out, there's going to be a couple associated here. And so this couple is going to rotate the ship back into its upright position. The problem is that if, for example, you had a ship with a metacentric height center that was at a different position, let's say under G. So if I redo this position like this, so we still have G here, center line here, and if it said M is around here, and my buoyancy center is, in which case it's around here, or in this case, because M is underneath G, the ship is going to rotate in the opposite direction, and so it's never going to. The moment the ship is going to have a slight disturbance, it's going to actually rotate backwards and it's going to fall into water and just simply capsize. That's why determining G for ships is very important. So yeah, you can think about it as rocking share of energy. So yeah, when the share in the back center moves, and so you have a opposite force that allows it, a couple that allows it to go back in its initial position. Okay, so that's what I talked about. So yeah, where it intersects, it's where it's called the metacenter M. And so, as I mentioned before, if GM is superior to 0, the ship is stable, which means that it will rotate back to its initial position. But if it's negative, it's simply going to capsize. Right. And there's a special case where GM is equal to 0, so the center of the metacentric center is the same as the center of gravity. In which case, even if you rotate the ship, it's going to stay in the same position. It's going to be like a neutral equilibrium any position you give the ship to the ship. So it's a bit of a special case. So so for ships, we need to determine the center of M, of course. So to do that, there's a special instrument called the stabilograph. So they use a pendulum. So all right, I'll just show you how it works. So if you take a ship, right, and we place, let's say, a weight in the middle of it, okay, a known weight. So the idea is that you place it first at the center. So you have your gravity center, of course, buoyancy center. And the idea is that you're going to shift the weight to one side of the ship. And so you have this pendulum on board. It's like this, I guess. And when you shift the weight, the ship is going to rotate, of course, because the center of gravity has changed to this G prime. So the pendulum is going to shift as well. So if we take the pendulum from its initial position to its different position, so this was the initial position of the pendulum, and now it shifted to this position. And so we know the length of the pendulum. Okay, so this is the length, and the deflection as well is known because there's a scale that allows us to measure the whole the deflection itself. Right, so we can calculate this angle since it's just tan alpha of the length, deflection, the deflection over the length, right? And so now if we look back at our initial G that was here, we know that there's a line here and there's a line here that intersects with M, right? So said otherwise, if you look at it this way, right? So what we want is GM, right? So as we saw before, we can write this as well as GG prime over GM, right? And GG prime, we can calculate it using it's known. It's like the formula, which is like this. So it's like the weight of the object we placed here times the distance we displaced it divided by the measured mass displacement of the ship. And so we can just have GM, which is like equal to the tan of alpha divided by GG prime. And that's how GM is calculated for ships. Well, there's another method as well, which is if you look at this image, you can simply write GM is equal to KB plus BM minus KG. So yeah, I mean it's a simple like addition of several parameters, and because we can also calculate them for ships. So KB is the height of the center of buoyancy above the baseline. BM is I over V, so moment of inertia of the waterplane area over volume of displacements, and kg is the height of the center of gravity above the baseline. So yeah, the particular thing about an object with a circular section, as we talked before, is that the center of gravity is always fixed. So even if you rotate the object, it's not going to go back in the initial position because the center of gravity changes with the objects, unlike the ship. So yeah, if you take a normal object G, and even if you shift it to the side, it's not going to change anything because it's round, right? So it's simply just going to rotate given the disturbance you give it, it's going to rotate with the certain force you give it. So it's not going to remain stable, right? Unlike the object he showed over there, because there's water inside of it. That's the main difference. I'll explain that later. And for an object with a square section, well, it's basically like a ship, so it's the same principle. So yeah, that was the method I explained earlier, is the inclining experiments with the pendulum and the scale, and with the displacement of the weights. So, and this is the stabilo-graph, which is used for measuring that displacement. So a reasonable amount of GM is about 3 to 5% of the beam. The thing is, you don't want GM to be too big or too small, because if GM is too big to be rotating with extreme force each time, because there's a big difference. If I represent that like so, if you take a ship and G is here and M is like over here, the problem is that once you have this small deflection of like alpha, it's going to give like much bigger difference between the buoyancy center. So the buoyancy center is going to be shifted by a bigger amount than it should be. So because of that, the couple exerted will be even stronger. And the problem is that if a GM is too small, then even if the ship shifts, it's not going to be rotated back to its initial position because the couple will be too small. So because of that, the ship will gradually just, if there's an excessive disturbance exerted on it, it will just gradually go sideways until it capsizes. All right, so the free surface effect is the idea of putting water inside the ship. So on the image you can see a ship where the water is contained, but if you remember the Titanic, it wasn't contained. So if we take let's take a basic ship that was built like in old times, I guess. So if you imagine just a ship with water inside of it because of a leakage, a flooding, or any other events that happened. If the water is this way, it's not going to change much. It's just going to add more weight to the ship. But the moment there's a disturbance, it's going to shift the center of gravity because the weight of the water will follow the shape of the ship. So the center shape, if the shape has changed, the weight of the water will automatically shift over here. And because of that, there's a new center of gravity, right? And so because of this new center of gravity, the buoyancy center itself has shifted, right, from this position, let's say, to like another position. That means the couple here exerted here is going to be much smaller than it should have been originally. So because of that, when there's water inside the ship will take a lot more time to rotate back to its initial position. And at some point or another, if there's too much water, it's just going to continue rotating to one side until it just capsizes. So yeah, having water in the ship has the effect of reducing the metacentric height because of this shifted center of gravity. And so, yeah, the ship capsizes to water in the vessel's 2 points. And so this is usually caused by flooding, liquid cargo leak, or unattended water. So, yeah. Same thing, if you lift the weight on the ship, you're going to shift the center of gravity, and the same thing, you can have a different couple between the buoyancy force and the center of gravity, which will more or less make the ship less stable. So we can actually estimate the range of stability because, as we said, the center of gravity can shift for a ship. So usually, well, I'm sorry, I wasn't very clear. So as we can see, if I take back, all right, let me just do a drawing again. So in this position, the buoyancy center is not here anymore. It's like around here, right? And so you can estimate the distance between the two. And so this distance, the greater it is, the more a couple is going to be exerted, right? So the more the ship is going to go back in its initial position or rock back in its initial position. The smaller it is, the smaller the couple will be. So you can estimate that for a ship. So the range of stability can be estimated for ships. It's different for every ship. And so you can trust, you can make a graph, and as you can see, there's a range of stability where GZ, which is the distance between the buoyancy center and the center of gravity on a horizontal line, is greater, is where the ship will be the most stable. So at 40 degrees is where the ship will rotate back in its initial position with the greater force. But as you can see, it'll go down after a while until it reaches like 70 degrees, which is the point of vanishing stability. And at this point, the ship won't rotate back because G and B are on the same line. And at this point, the ship will just stay in this position until it gets filled with water and just simply drowns. It should be noted that the steeper this slope is, the better it is, because we want a big distance gz, because the bigger the distance gz, the bigger the couple, and the bigger the couple, the faster the ship will reorient itself in its original position. Okay, so you can also estimate longitudinal static stability, which is like the stability for the ship, but instead of looking at it sideways, you look at it from a different perspective. So same thing, you have to be careful about not putting too much weight at the front or at the back. So yeah, the ship rarely capsizes from due to this, but you can still like remove or shift ships between the two. Yeah, so to be careful, you have to be careful. So yeah, so due to hull damage, you have water that goes into the ship, and this water causes more weight, and weight causes this increased instability, and then this instability just after a while just causes the ship to capsize. So to prevent that, nowadays there exists bulkheads. So these are kind of walls that increase the structural rigidity, and they create watertight compartments. So that means that if water is leaked inside the ship, it only gets leaked into one compartment. So and that compartment itself is not very permeable. So it means it's resistant to water, which means the water only stays in our compartments. And so because of that, it allows us to like limit the damage that water can do. So yeah, one compartment standard, and you can be. So yeah, the idea is that to prevent the ship to capsize. So if the compartment is flooded, yeah, the buoyancy provided by that compartment will be lost, and the weight of the ship will increase, and so the ship will sink deeper in the ocean, and then after a while, if the ship is rotating too much to the side, and it'll just sink. So you can also estimate the permeability for a compartment, which is pretty important if you wanna make sure that your compartment is non-permeable. So the idea is that you want it to be resistant to water. So there are typical values for ships in certain areas, because certain areas are more vulnerable to water. So you have to make sure that they can hold a bigger amount of water. And so now we can talk about submarines. So there's two types of stability. There's the submerged stability for the submarine and the surface stability. So we talked about this earlier, but the submarine has ballast tanks on each side, and the idea is that both of them fill up at the same time, and the water will be all around the ship, so that the only top will have no water, so that way that the top will actually remain stable and won't capsize. So when it's submerged, it's kind of the same for a ship. It's a lot less stable though, so you have to be even more careful. But yeah, the idea is the same. And for the stability of a fully submergible body, since the ship is underwater, the center of buoyancy never changes, right? So it actually coincides with the metacenter. And so that's why you can just say that GM is equal to GB, because B is equal to the metacenter. And you have to be careful that B must be above again G for stability, because otherwise the submarine will just rotate backwards and will just be upside down.